Integration, an inverse process of differentiation. In the previous two chapters, we studied continuity and differentiability, and then we studied application of derivatives. In continuity and differentiability, we studied about how to find the derivative of a function using different ways, that is by substitution. Then we studied parametric differentiation, then we studied higher derivatives and many other things in that chapter. And when we studied application of derivatives, we learned how to approximate, what is the rate of change, then we learned maxima, minima, and also increasing and decreasing functions. So these are the many things that we learned in differentiation. Now this chapter, why did I tell about differentiation in integration at the beginning itself? Because integration is actually, as the heading says, the title says, it is a reverse process of differentiation. And how is it the reverse process of differentiation? We will be looking that in this video. So let's draw a graph over here. And I have this one over here, marking 1, 2, 3, 4, 5 on the x-axis, and on the y-axis again 1, 2, 3, 4, 5, 6 on the y-axis. So I have the x and the y-axis marked over here, and now on this I have a line. So this line is like this. Okay, so I have a line over here. Take this as a graph. Now what will be the area of this graph? What will be the area under this graph? If I shade this area under the graph, it is going to look like this, right? This is the area under that green line that I have drawn. This line is enclosing what? A rectangle. Is it enclosing a rectangle? Yes. It is enclosing a rectangle. And what is the area of this rectangle? The area of this particular rectangle is nothing but the length into breadth. And what is the length here? It is 4 and the breadth is 3. You can see that this is 4 and this is how much? 3. So you can say it is 4 into 3 or 12 square units. So what I have got here is the area under this graph. That is, this is a green line, and that green horizontal line is enclosing an area of what? 12 square units. Suppose I have another graph which is looking not like a single straight line, but it's a combination of another line also. So you have another line which is looking like this, the part of the graph. Okay, so now you have this graph, and what will be the area of this one? Can you find out this area just by using the same way that we did for the rectangle? No, not directly, but there is another way that I can do this. Can I just split this into one rectangle over here and another rectangle over here? Can we see two rectangles? Yes. So if I shade this one, this is one rectangle, and here you can see another rectangle. So how many rectangles do you have here? You have two rectangles over here. Now, what is the area enclosed by this entire graph? Suppose I am taking this as a function y is equal to f of x. What is the area which is enclosed by this function f of x? It will be nothing but the sum of areas of the two rectangles. And what is the sum of the two areas? The first one will be how much? As we said earlier, this is 4 and this is 3. And the same goes for this one. This is how much? 6 and this is how much? 2. So the area will be, the total area will be nothing but 4 into 3 plus 6 into 2, that is 12 plus 12, or that is 24 square units. So now I have found out the area for this graph also. Now you might be wondering, I started with integration, then I'm going to find out the area under two rectangles. First one, it was a simple rectangle, and now we had two rectangles over here. What is the use of all this? Let's try with another curve. Then we might find a conclusion for that. So there is another curve that I'm going to draw, which looks like this. So this is the function that I have drawn here, that is y is equal to f of x. So I have a new function here, which is y is equal to f of x. Now, what will be the area under this function, that is y is equal to f of x? In case of rectangles or in case of straight lines, it was easy to find the area. Just take the rectangle, use the formula to find the area, got the answer. That is the area. Now, what will be the area of this curve over here? Same way we found out the area of the rectangles. Can we divide this into different rectangles? If I draw dotted lines over here, I can see that this is divided into how many? 1, 2, 3, 4, 5, 6. It is divided into 6 rectangles. So almost a rectangle, not an exact rectangle. You can see that there is a slight difference over here, here, here. So it's not a perfect rectangle, but it's almost looking like a rectangle. So I can find out the area under this graph by dividing that into small rectangles. Yes. So instead of this, if I take another, suppose I'm drawing another graph over here, and the same graph is here. Now if I divide this graph into smaller rectangles, very small rectangle parts, suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have more rectangles. So when I have more rectangles, what happens is I get the area into a more accurate value, right? Yes. Because when I take into smaller rectangles, what happens is this space over here, this gap over here, you can see there are small gaps over here, right? This gap is this one. So what happens is when I divide that into more number of rectangles, when I increase the count of rectangles, these small gaps gets decreased, or you get a more accurate value for the area under the graph, which is f of x. So that is what is going to happen when I divide it into more number of rectangles. Now let's keep it for this one, this figure itself. As I can see here, what is the first one? You can take that is 1 unit. So I am not going to find out the exact area under this graph, but I am just going to take this part, small part here as delta x1. What is it? Delta x1. It is a part of the which line? X-axis. And from that I am taking another part. So it is delta x1. So what will be the second one? It will be delta x2. And till that last one, here it is 6. So I can put it as a delta x6, or if there are n number of rectangles, if there are so many other rectangles, you can take it as delta what? Xn. So you have different numbers of rectangles. So delta x1, delta x2, delta x3 up to delta xn. Now this function over here, if I am putting it as f of x1, f of x2 into different values, what is the area of each small rectangle? What is the area of one rectangle? Can I take the area of one rectangle to be, suppose this is delta x1 and this is f of x1. So what is the area of a rectangle if it is length into breadth? Can we write it as f of x1 into delta x1? Yes. Same goes for the second one, that is f of x2 into what? Delta x2. And like that it goes till f of xn into delta xn. So in this way, if I divide this into n number of rectangles, I can find out the total area by using this way. Or can I simplify it more? Yes. How can I write this again? I can write this more simplified as sigma I equal to 1 to n f of xi into delta xi. So if this way, if I write, I can simplify it more further, right? And say that this gives the total area which is under the graph. That is f of x. Now again the question comes, what is the use of integration here, or why we are discussing this over here when we start talking about integration? Integration is not like differentiation. Integration finds out the area under the graph. So what does integration do? It finds out the area under the particular function that you are integrating. So integral will give you the area. Differential or the derivative is not giving the area, but it gives the slope of the tangent which is passing through that particular point, or in general whatever point it is there. So differentiation and integration are not same, but it is a reverse process. Now what is this reverse process? We will discuss later in the session itself. But for the time being, understand, integration is actually finding out the area under curve. Now the next question is this a way that we are going to write this entirely in this chapter? That is sigma I equal to 1 to n and from f of xi into delta xi. Is this the way that we are going to write? No. So what I'm going to do here is, I'm going to draw another graph. So you can see another graph over here. Another, that is y is equal to f of x. Now I am taking two boundaries. One is A and the other boundary that I am taking here is B. So I have two boundaries, and if I want to find out the area between this A and B, let me just shade that area. So I have the area between A and B, yes. Now, how to find out the area? Same way that we just found out the formula. What is the formula? Just rewind that formula, that is sigma I equal to 1 to n f of xi into delta xs. This is the formula that we have just found out. Now this formula can be more easily written in another way, that is by using the integration that we are learning in this chapter, right? So what is the way? It is actually the integral symbol. This looks like this, and what is the boundary? It starts from A and ends at B. So under that symbol put an A, and on top of that put a B. So how do you read this? Integral A to B. So you are finding the integral A to B, or you are finding the area from what? A to B. Of which function? The function is f of x. So integral A to B f of x, and with respect to what? X. So you are having the area of this function, which is found out using integral A to B f of x dx. So now we have understood what is the formula to find out the integral. So now, how to do that? That is a question, right? You cannot just simply put the formula and say, this is the integral, that is the integral. You need to know what is the actual integral of the value. Now, listen to the title again, that is integration or the reverse process of differentiation. So let's discuss the differentiation again over here. So now we have d by dx. We know that d by dx of sin x is nothing but what? Cos x. So d by dx of sin x is cos x. Now, d by dx of log x is 1 by x. Yes. And the same like that, if I write d by dx of sec x is sec x tan x. So you have the derivatives of three different functions that I've written here: sin x, log x, and sec x. Now, what will be the use of these derivatives when I'm talking about integration? Reverse process of differentiation. So if I take cos x, if I take what? Cos x and integrate. So I take cos x and integrate. So integral cos x dx will be nothing but what? This sin x. So integral cos x dx will be sin x. Okay, it's not over, but I'm just writing for the time being. Integral cos x dx is what? Sin x. The same way if I write integral 1 by x dx, is that log x? Yes. And same way integral sec x tan x dx, I can write it as what? Sec x. Okay, understood? So this is just the basic way of understanding what is the difference between differentiation and integration. If you differentiate a particular function, that is if I differentiate sin x with respect to x and I got cos x, and now if I integrate cos x with respect to x, I will be getting what? The opposite, that is sin x. Clear? And the same goes for log x. If I differentiate log x with respect to x, I get 1 by x. Now if I integrate 1 by x with respect to x, I get log x. Goes for sec x also. Sec x tan x, integral will be sec x itself. Now there is another confusion that comes up over here. I have taken in the beginning d by dx of what? Sin x. Now instead of this one, if I take d by dx of sin x plus 10, what will be the derivative of sin x plus 10? Again, that will be cos x itself. Because you know the derivative of a constant is always 0, so you don't need to take the derivative of 10 and write it as 10x or anything. That is simply 0. So sin x plus 10 will give the derivative what? Cos x. So if I integrate this cos x, again, should I be getting the sin x plus 10? Yes, it can be sin x plus 10. Again, look here, d by dx of sin x minus 5. What is the derivative of sin x minus 5? That is also again cos x, because minus 5 is a constant, so leave it. So you got cos x. Again, if I take this cos x and integrate, I will be getting integral cos x, or integral, not simply cos x dx. So integral cos x dx is what? Sin x minus what? 5. So integral cos x, 3 times in this screen you can see integral cos x. So 1 over here, right? 1 over here. And the other two, this one, there is another one over here, and another one over here. So you can see 3 times I have written this cos x, cos x, cos x dx. So it has sin x at the first time, yes, and now you have sin x plus 10, yes, and you have sin x minus 5. So what does this suggest? A particular function, when you integrate, can give different outputs. Yes, it can give different outputs. It need not be always the same. But when it comes to differentiation, when you take a particular function and differentiate, will you get multiple differentials or multiple derivatives? No, you won't be getting multiple derivatives. You will be getting a single derivative. But that is not the case with what? Integration. When you integrate a particular function, you can get multiple outputs. And these multiple outputs, since there are multiple outputs, what we write is, we take integral f of x dx and we write the integral as capital F of x plus c. We always put a constant. So what do? We always put a constant along with the function or the integral. So you got integral small f of x dx, which is equal to capital F of x plus what? C. So same goes for which one? The example that we discussed, integral cos x dx will be not sin x plus 5, not sin x plus 10, not sin x plus 100, not anything, right? So what we do is we write a capital C along with it. So what is this capital C? It talks about the constant of integration. So this capital C is nothing but the constant of integration. Understood? So this is very important when we talk about integrals. You cannot say the value of the integral by just writing sin x, that is integral cos x is equal to sin x. It does not give the final answer. So to get the final answer, you have to write integral cos x dx is equal to sin x plus the constant of integration, that is c. Now what is the value of this c? It changes. Yes, from 10, from minus 5 in the previous slides we saw that it can change from any value. So we don't need to bother about that constant of integration for the time being. Just write it as what? Capital C. And writing that capital C is very, very important when it comes to integration. Got it? Now, another graph that I'm going to talk over here is x square. Suppose I have y is equal to x square. So I draw this y is equal to x square like this. Okay, there is a graph y is equal to x square. Now there is another graph y is equal to x square minus 10. So that graph might look like this. There is another one, y is equal to x square plus 5. So that graph can look like this. Yes. And another one, y is equal to x square plus 10. So that one might look like this. So there are 4 different graphs that I have drawn over here. That is y is equal to x square, y is equal to x square minus 10, x square plus 5 and x square plus 10. Now if I take a line, now what I'm going to do here is I'm going to take a line x is equal to a. So if I take x is equal to a and I draw that along over here, I might get something like this. I might get a line which is passing like this. So look here, at all these passing points, I can see there is an intersection point. There is another one over here. There is one over here. There is one over here. There is another one over here. So this line x is equal to a. I'm not taking x is equal to 1 or 2 or anything. I'm just generalizing it and saying it is x is equal to a. So what happens is, at this point, at this line, x is equal to a. There are different intersection points, and because of the different intersection points, there can be different tangents which I can draw. Yes. So if I draw a tangent over here, it might look like this. Another tangent over here, it might look like this. Another one over here, that might look like this. And the last one can look like this also. Okay, so there are different tangents which I have drawn over here on these intersection points. So what happens is, when I try to find out the slope of the tangent, are they all same? Let's see. Because it is y is equal to x square, the derivative dy by dx will be 2x. And since it is passing through the line x is equal to a, what will be the derivative dy by dx at x is equal to a? It will be 2a. So the derivative at the point or at the line which is intersecting all the curves y is equal to x square or x square plus 10 or x square minus 5 or anything, the derivative of all these functions will be what? 2x itself. Now, what is the slope that I get? It is 2a. So as you can see that this slope of the tangent is same for all the curves. But is the equation of the curve same? No. What we can understand from here is integral 2x dx can be x square or it can be x square minus 10 or it can be the third graph x square plus 5, or it can be x square plus 10. So the integral can change. So in general, can I write it as x square plus c? Yes, we can. So this is the way that we write the integral. So integral of a particular function can be anything, but the reverse, that is the derivative of a particular function cannot be anything. It has to be a particular fixed value only. Understood? So that is what we arrive to a conclusion between integration and differentiation. Okay. Now there are some more standard integrals that we have to study before winding up the session. And what are they? So the first one is d by dx of sin x. We know that d by dx of sin x is what? Cos x itself. So what will be the integral of cos x? Integral of cos x dx will be sin x plus c. Yes. Same like that, d by dx of cos x will be minus sin x. Now what will be the integral of minus sin x dx? It will be cos x plus c. Okay, do write this down along with this. And same like the d by dx of tan x is sec square x. So integral sec square x will be tan x plus c. D by dx of cosec x will be minus cosec x cot x. And so what will be the integral of minus cosec x cot x dx? It will be cosec x plus c. So that is what we get for the integral of minus cosec x cot x also. And when we talk about sec x, the d by dx of sec x will be sec x tan x. Now what will be the integral of sec x tan x dx? That will be equal to sec x plus c. And there are a lot more other integral values also. So I'll just give you an idea about all that. Do write this first. Integral x raised to n dx. Integral x raised to n dx will be x raised to n plus 1 by n plus 1 plus c. Integral x raised to n dx will be x raised to n plus 1 by n plus 1 plus c. Do remember all these values, very important. And when we talk about integral e raised to x, the integral of exponential function will be e raised to x only, so e raised to x plus c. Now integral a raised to x dx, what is that? It is a raised to x by log a plus c. And now integral 1 by x dx can be written as what? Log x plus c. So these are the different standard integrals that you have to remember in this first session in integration, because for the continuing around, we have a total of 10 sessions in integration, and for the remaining 9 sessions, these basic or standard integrals are very important and useful. So do remember, do write this down somewhere and by heart these formulas, as it is very important. Now, what happens is, next one, instead of integral sin x dx is nothing but minus cos x plus c. Now what will be integral sin 2x dx? What will be this value? Is it as easy as integral sin x dx? Or is there something different? And same for integral log x dx. Is that also same as derivative? How to find the derivative of log x? 1 by x. Is this the same as 1 by x? No, there are some changes in that, right? We will discuss those changes, and we will discuss what is the difference in integral sin x and integral sin 2x in the next session. Until then, keep exploring.
Manorama Horizon. Learning made simple.